Today I'm going to talk about graph-based change propagation across BIM design software applications. It's a collaboration study done by Tekla and Trimble. Since the industries many fragmented and federated, like taking the design phase as an example, it involves many experts like architects, engineers, and everyone works on their own models. Like architects has an architecture model, structure engineer has a structure model, and MEP have MEP model. And those models are constructed, developed by different software, and those software does not talk with each other. So how can they collaborate? The latest cloud collaboration technology for multidisciplinary design is file-based common data environment, in short, CDE. CDE basically provides a cloud repository that everyone can exchange files with the CDE. So usually the design starts with the architecture. So the architects upload the first version of the architecture model. This will be reviewed by BIM manager or coordinator. Ensure everything is fine, this model will be released to engineers. Engineers will load the architecture model in the background as a reference model and create their engineering models. And after finishing the engineering, the first version of the engineering models, structure models, MEP models, they will upload the model into the cloud again. And the BIM manager will take all the files for clash detection and inform everyone to improve their works. Then another round of the design will continue. The architects will upload another modified version of the model, and this model will be compared by the BIM manager and tell everyone which is modified, and everyone will load the latest version of the model again, trying to improve their version 2 model. So on and so on, this design phase will finally finish. As you can see, this is a file-based sequential design. You need to wait for a long time. And a lot of steps need to check manually, and the users need to resolve all these conflicts manually. And BIM managers need to compare those models and inform everyone the changes, as well as we need to control all the versions by ourselves, which is really cumbersome. But if we look outside of the BIM domain, for example, we use Microsoft 365. It already allows us to collaborate in the same document from different devices on the same file. Similarly, in the manufacturer domain, they have Onshape. It has similar functionality that can allow users to access the same model and modify at the same time. There is some difference between the mentioned examples and the BIM cloud collaboration. In the mentioned examples, they use single software, they rely on single source of data. However, we have so many different types of software, and everyone has its own model, so we rely on heterogeneous data. The latest CDE technology just place the files in the cloud already illustrate it has very limited functionalities and intelligence. Therefore, our research, we are going to compile all this information from files as graphs. Every domain has its own subgraph, and use machine learning to link the objects inside each graph together and obtain a linked graph. After that, we can track the information that you modified in one domain and propagate this information to another domain due to the explicit generated or cross-domain relationships. We named this research CBIM, Cloud BIM. So user design in local software, we use CBIM connector to compile the information as graphs and send to the cloud server. We do the same thing for all other domains. We have architecture subgraph, structure subgraph, MEP subgraph, so on and so on. Then we use semantic enrichment algorithms to link those graphs together. Those relationships could be topology to describe their spatial relationships, could be functional semantics, as well as design intent and constraints. For example, there is a wall, but the wall in different models have different representation. Therefore, we put the CBIM corresponds to relationship between the architectural and the structural wall. Additionally, engineers put the MEP radiator on purpose too close to the architectural wall. Therefore, we generate CBIM attached to relationship to illustrate the design intent behind the engineers. After we got the linked graphs, we are going to manipulate the linked graph, such we imply the consistency maintenance mechanism on top of it. In short, CBIM uses graphs to compile information. We link those subgraphs, and we are going to apply intelligent functions on top of the linked graphs. Let me show you our experiment. We select architecture Revit and structure Tekla. And we also developed our own CBIM server to connect between the local software. We constructed CBIM Revit connector, which can extract data from Revit, can communicate with the server, and is compiled by Dynamo and Python. Similar for Tekla, we constructed CBIM Tekla connector, which is compiled by C# and Tekla Open APIs. In the middle, the CBIM server, it has a data layer to store the graph-based data. It also have an algorithm layer which can employ those rule-based algorithms to instantiate those across-domain relationships as well as a consistent maintenance mechanism. It's compiled by Python. So here is the first prototype, which is change propagation across BIM applications. We are going to show you users' graphs. How can we propagate the change in one domain to another one? This is an example model from Revit, and we select part of the model. The architecture model is placed in Revit. The structure model is placed in Tekla. Now the architecture model decides to change the model, and after finish the modifications, the architects upload the model in the cloud. And we already generate all those graphs in the cloud, and the cloud identify the changed objects from the architecture is architecture wall. And then the architecture wall already has a CBIM hosted relationship with the structure column. Additionally, this kind of object, the wall and the column, is already inside the prepared related object list. After meet these two conditions, CBIM server understand we need to do some action. So it prepares some change propagation commands and sends to Tekla structure. Correspondingly, inside the Tekla, if the user clicks receives from CBIM, and then the CBIM will load the changed object geometry in the Tekla structure directly. And this can help the structure engineer to identify the change from the architecture model, also to assist the design. Let me show you another prototype. The first prototype only show you geometry change, and now we are going to show you consistent maintenance, how we can use graphs to even promote some proactive suggestions to help you maintain the consistency of the models. There is a project have an architecture model and a structure model, and this model has been linked well in the cloud server. We even generate constraint relationship. For example, the structure slab 1 has CBIM exact geometry special constraint with the architecture slab 1. It means that the architecture slab 1 should contain the structure slab 1 in the XY dimension. Currently, this constraint is satisfied. Constraint is kind of like the user experience, but explained in a graph and in a machine understandable language. And this can help the machine, can help the computer to maintain the model if something is violated. For example, now the architects decide to move the wall. After finishing the modification, the architects push the latest version of the model to the CBIM server. CBIM server receive the change, identify the change, and also find out the violation, and start to compute the suggestions how to make those two models consistent. Correspondingly, in structure model, CBIM provide proactive suggestions. Here, we move the columns and the beams automatically, of course, with the permission of the structure engineer. For some kind of change that cannot be handled by CBIM right now, we also provide changed object geometry, such as a brown bottom slab, like here, so which is here, the brown slab, which can help the structure engineer to know where is the latest change of the architecture model and help them to improve their design. So this research is still ongoing. We have some limitations. First of all, we only explore a few classes of design internal constraints, and all those cross-domain relationships are generated by rule-based algorithms. And the illustrated prototype currently can deal with translation conflicts, but other conflicts are still beyond our ability. And from some engineering perspective, all those converters, all those cloud servers are in laboratory conditions. It need to be developed more to be more robust. So here is also inspired us to research more. In the future, we are going to invest and design an ontology. It could be the first ontology which is going to encapsulate the design intent constraint relationships as a class level inside the graph. And we are also going to explain using graph learning to generate those cross-domain relationships. But then it raises another question: how BIM models is suitable for machine learning? So we are going to leverage all those, we are going to explore, leverage all those BIM data, including geometry, attributes, relationship in graphs, and make the graph is more suitable, like property graph is more suitable for machine learning. So in short, facing the federated nature of the ASCE industry, the existing file-based common data environment collaboration is still really cumbersome and needs to execute it many steps manually. So we are going to design a more intelligent and close collaboration platform in the future. Here, we propose a graph-based approach which can represent and link building information for supporting or cross-domain intelligent applications. And we also demonstrate two CBIM prototypes. The first one, the change propagation, like to propagate the changed objects from one domain, one software to another one. And the second one is proactive consistent maintenance, how the graphs can help us enable intelligent applications to maintain the consistency of the model. In the future, we are going to explore more about graph machine learning by integrating multiple types of BIM data into graph format. And we are also going to explore using GNN to instantiate multi-class or cross-domain relationships. Thank you very much. This research received funding from EU Horizon 2020, and there are some publications. Welcome to visit us. Thank you. Sure.
Yeah, you go ahead.
Oh, sure.
Had a nice presentation, and it is quite interesting to use graph because it is different to the previous approach. So maybe I have two questions. One is what you have in server basically a top-down approach. Like for example, everything is from architect and then drop down to civil or MEP engineer. So do you have any like feedback from bottom up? Like for example, if architects move this and then somehow structural engineers say you can't move this, basically you need to apply to the structural base and we need the column here, for example. So do you have any approach that from bottom up?
Yes, we do consider this. This is related to my colleague Mia's research. Basically, we consider this collaboration, it's not linear. So we will have a mechanism which is going to, like everyone can participate and can reject your modification.
Yeah, and maybe the second thing, so everything in this graph approach is more on object oriented, if I'm not wrong.
Right.
Do you consider in the future development for task-based oriented? So for example, it's like the stakeholders need to have a requirement, and then according to this requirement, what architects done for that, and then what structural engineer was done for that, because it is quite, in the standard industry, we usually just take out the requirement as a task-based rather than object-oriented based. So do you consider any future development on task-based graph rather than object-oriented graph?
That's a really good question. So basically, we consider that. So we consider that to be part of the CBIM methodology. So meaning that this kind of requirements could come from user experience, could come from user order codes. So this will be generate some task nodes, not the BIM object nodes, trying to deal with the problem. Thank you.
So the graph gives you ability to study topology of the graph. Do you consider connecting topology of graphs from different models that might help connect them in a better way?
I think that, so you are going to ask what's the advantage of graphs if it has an advantage to show the topology. Yes, graphs do have the advantage to show the topology, but the most important thing we think is that graphs can show the relationships between objects explicitly. And these relationships is really hard to be represented in other formats, like in images or in tables. But in graphs, it's a very natural thing. We can show the relationship across objects. Thank you. Yeah, please.
Thank you both for that. Quick question. So, in your case study, are the architectural model and structural model created separately? Like, then they communicate through a central cloud? And I was wondering, is there a way to like have a central model, then they can generate architectural model or structural model? Is that possible?
Oh yeah, I think yes, that's totally possible. But according to the culture of this industry, especially the publish of the standard ISO 1965. So previously, like the industry, my understanding is still trying to want to explore whether we can rely on a holistic model. Everyone work on that, it will be easier. But it turns out, like the culture of the industry is still very federated. They prefer to keep their own models. Architects keep the architecture model, structure keep the structure model. So it includes, like, it raises the problem or the difficulty of the collaboration that we face today. So actually, I think it's a very industry-specific situation for us, for BIM. Yeah.
Great, thank you so much.